Yes.
Okay, just before we begin our last talk for this session, let me just,
I feel like
there will be a reception afterwards across, in the coffee break room. Before that, I think it would be nice if we can get just sort of a workshop picture. And so after Sunjin's talk, maybe everyone could come up to the stage and we just take a picture or two, something like that. So our talk will be by Sunjin Choi. He'll tell us about Fortuity and hairy black holes in AdS.
Thank you very much. Sorry. I would like to first thank the organizers giving me a chance to speak at this wonderful workshop. Today I will talk about Fortuity and hairy black holes in AdS based on the 3 papers. The first paper is about constructing supersymmetric hairy black holes in the bulk AdS with, most importantly, Venice and Chintan here. And these 2 papers are about studying fortuitous operators of n equals 4 per Young mills with one of my great collaborators here. So I want to talk about, of course, black holes, and especially there have been lots of progress on understanding supersymmetric black holes in AdS5 CFT4, as we heard from many talks in this workshop. And today, my goal is to illustrate our proposal on supersymmetric phases of quantum gravity on AdS5 times S5 and for the n equals 4 super Young mills. So what does it mean by supersymmetric phases here? So supersymmetric black holes in AdS5 times S5 carry 6 conserved charges. Of course, they should satisfy the BPS relation given as this. So energy is given by the sum of its electric charges and angular momenta. But you can also find some these 5 conserved charges satisfy some nonlinear relation to avoid closed time-like curves. You can understand it easily see from this figure. So we first fix the angular momentum, and the x-axis is the charge, and y-axis is the energy. So this blue line is the BPS line. And also you can draw the extremal line for the Kerr-Newman black holes, and you can see that it only overlaps only at a certain point, and this is nothing but the nonlinear relation between the charges. So you can ask, and you can see that so there is no supersymmetric black holes except for this point on the BPS surface. And furthermore, you can see that there is a gap between extremal black holes and BPS black holes. And also, this gray region is where the nearly extremal black holes suffer from dynamical instability due to superradiance. So you may ask that, what is the origin of this gap and this charge relation of these supersymmetric black holes? One direction might be to explain from the field theory side, to explain the absence of macroscopic degeneracies in the gap here, and also the charge relation from charge relation. And the second direction will be find new black hole solutions in AdS5 times S5, filling this gap, and also the other part of the BPS surface, and possibly replacing this unstable nearly extremal black holes. And today I want to talk about our proposal toward the second direction. But unfortunately, I will not talk about the finite temperature black holes due to the time limit, but I will present our result on the BPS surface so that our supersymmetric hairy black holes will fill this entire BPS surface. So how can we construct such a supersymmetric hairy black holes? Maybe one can just start from constructing solutions in the gravity side, but today I want to start from the CFT duals and study the operators dual to the black hole microstate, which we call fortuitous operators. So study their characteristic properties, and using such a properties, we would like to construct the supersymmetric hairy black holes in the gravity side. So, as in many talks today, we already somehow learned that black hole microstate is very different from the graviton states. The characteristic properties of the black hole states are now named as the fortuitous property. And I want to study how can understand some emergent geometric description from such fortuitous operators, and how can we construct new black hole solutions based on these fortuitous operators. And today I want to show you that we can make these two kinds of hairy black holes. I will show you later. So we want to study strongly coupled gauge theory to study semi-classical gravity in AdS. So in order to study strongly coupled gauge theory, we will focus on the BPS sector, in which we know that certain operators are protected, meaning that they do not receive anomalous dimensions and strong coupling. Also, we'll study the finite N gauge theory, not large N today, which means that Newton constant in the gravity dual is finite. But as we heard from some other talk, even in such a theory, we can distinguish between graviton and black hole states using this fortuitous mechanism. And these finite and black hole states can be thought of as some quantum black hole in AdS. And I will explain you that they exhibit certain properties of semi-classical black holes, so we can get some lessons of black holes in AdS from these fortuitous operators. So we'll study 2B string theory on AdS 5 times S5 holographically from Fortuity equals 4 super Yang-Mills. And actually, the setup is already explained by various talks today, so I will just very briefly explain my setup, but just please interrupt me anytime if you have any confused things. So we will study the 16 BPS operators, which is annihilated by one Poincare supercharge and is Hermitian conjugate, this conformal supercharge. And our Poincare supercharge satisfy the following superconformal algebra. And our BPS operators will satisfy this BPS condition from this superconformal algebra. So its scaling dimension will be given as the sum of its arc-charges and angular momenta. And from the free theory, we can easily write down the letters satisfying this BPS relation. We have 3 scalars, 3 Carolinus, 2 gauginus, and anti-self-dual part of the field strengths, and you can act arbitrary number of holomorphic derivative on them. And you can multiply these operators, and you can act arbitrary derivative on them, which will give you the general gauge invariant local BPS operator in the free theory. As you heard many times today, these supercharger received quantum corrections, firstly at one loop order, meaning that lots of BPS operators we constructed in the free theory acquire non-zero anomalous dimension at one loop level. And the conjecture was there will be no further corrections in the higher loop and non-perturbative, but as beautifully reviewed by Qiming's talk today, recently people found an explicit counterexample. So if you consider 16 BPS sector of 4D equals 4 SO7 super Yang-Mills, you can show that a pair of one loop BPS operators are lifted at 2 loop order. And furthermore, the complete one loop corrections to the supercharge has been studied recently by Kasia here and her colleagues. Nevertheless, we have seen that the index correctly captures the entropy of BPS black holes, meaning that there should be a macroscopic number of protected operators which do not receive anomalous dimensions at strong coupling to explain the entropy of BPS black holes. So these protected operators will be holographically dual to the microstates of black holes I want to study. So we shall construct candidate BPS operators dual to black hole states at one loop order, and hoping that maybe they will persist to exist at higher loop. Fortunately, our candidate one loop BPS operator is shown that they really do exist at arbitrary higher loop order. I will explain later. So with this assumption, let us start our program. So we want to study 16 BPS operators which are analyzed by Q and Q dagger and by standard Hot theory. You can map to Q cohomology classes, which is Q closed, but not Q exact. And you can write down the tree-level Q action or classical Q action on free BPS letters I already introduced. And now at tree level, only phi and lambda are annihilated by supercharges, but the other letters and also covariant derivatives do not vanish under the action of supercharges. So our goal is to construct representatives of new cohomology classes made by these letters, which are not of graviton type. So what is the cohomology? Okay, before going into the detail, any questions about this setup? Of course, you may have already heard so many times about this setup today, but okay. So graviton type operators can be constructed in the following way. So in the gravity side, the BPS graviton state. What I mean by graviton is basically all, not only gravitons, but all perturbative particle states like scalars, fermions, photons in the gravity side, and they can be defined at 0 Newton coupling in free theory. And one can find local BPS operators in super Yang-Mills due to such states at n equals infinity, which carry finite energy. And you can show that they persist to exist at arbitrary finite n. So if you construct these operators as n equals infinity, you can just use them at arbitrary finite n. They remain to be BPS. So these are the graviton cohomologies. And because of the behavior, actually I got these figures from Chiming's paper, but so these graviton operators, the anomalous dimension of graviton operators does not depend on n, so usually people call it as monotone operators, but however, in the gravity side, we know that there exists supersymmetric black holes which carry to the n square number of states. So we should find it to the n square number of dual BPS operators in super Yang-Mills, which carry n square in each state. And since we know the monotone operators, number of monotone operators does not scale does not scale exponentially, so we should find extra BPS operators at finite n. And these operators become BPS only at finite certain n due to trace relations, which we now call it as fortuitous operators. And they will be dual to the black hole microstates in AdS5. And let me show you the example. So for the graviton cohomologies or monotone operators, you can start from the single trace. So the superconformer primary is given as a symmetric trace of n number of scalars. And you can consider superconformal descendants using fermionic generators, which commute with our chosen supercharges to define our cohomology problem. And these cohomologies can be arranged into certain short multiplet called Sn. And they are shown to be absolutely protected. So they will persist to exist at arbitrary coupling, arbitrary finite coupling. And for S2 multiplet, which means that we only use 2 letters, the conformal primaries are given as this. So you have symmetric scalars, scalar times gaugino bilinear, and scalar times Carolino, and so on. And multiplying above operators will give you independent multi-traced cohomologies at large n. And this will explain all the single and multi-particle graviton states in AdS5. However, if you move on to the finite n, as I said, the formal construction gives cohomologies at arbitrary n, but the thing is that they are not all linearly independent. The number of independent operators reduces due to the trace relations when the number of fields becomes larger than n, basically due to the Cayley-Hamilton theorem. So in SU2, I think you already seen this equation, but if you multiply trace x squared times trace y squared, and you can see that actually this is equivalent to the square of trace xy. So the number of independent operator reduces in the field theory due to the trace relation, and actually it is also understood from the gravity side as the stringing exclusion principle. So in AdS gravity, if you increase energy of the gravitons more than n, and it has been known that they are polarized into the distributed giant gravitons, and this procedure reduced the naively counted the number of states. So these kind of monotone or graviton operators are well understood, and but we know that there are certain other operators responsible for the black hole entropy. So our goal is to find the novel finite element cohomologies which are not of graviton type, which we call fortuitous or black hole cohomologies. Any questions? Okay, so in order to find such an operator, I like to start from the index. So we want to consider the superconformal index, the Witten index type thermal partition function on S3 times R. And this index will count the number of BPS operators with -1 to the f. And the nice thing is that this is protected under any continuous deformation, so we can exactly compute this index at weak coupling to study strong coupling dynamics. And our strategy is the following. We first, let's say, compute this index order by order. And also, since we know the definition of all graviton cohomologies, we count the number of independent graviton cohomologies at finite n at order by order charges. So we can compute the finite n graviton index and subtract the graviton index from the full index will give you the number of black hole fortuitous cohomologies. Basically, we are computing the black hole index or fortuitous index. However, it turns out that this problem is a bit technically difficult, so we want to truncate our problem, which already introduced in Sun's talk. So we want to truncate our classical cohomology problem into the sector with no derivative. So without derivative, the problem becomes much, much easier. And since you do not excite any derivative, you should also not excite gauge-ino, since the Q-action derivative will give you gauge-ino. So you can only excite scalars, Carolinos, and field strengths, and these give you the closed subsector of our classical cohomology problem. And these fields are the fields excited in the BMN matrix model, so we will call this as the BMN subsector. And for your information, I wrote down their Q actions again here. And I would emphasize that this BMN subsector is already very non-trivial because you can show that the index over BMN cohomologies exhibits n-square entropy at large n. So even inside this subsector, you have black hole entropy. So you have many, many, many number of fortuitous operators corresponding to the, at least some part of Bekenstein-Hawking entropy of black holes. So yeah, and for
the microcanonical or the saddle point?
Sorry?
Are you talking about the saddle of this index or the microcanonical?
You can just find the saddle point in the large n.
I see. But it doesn't have a minus sign, like it's a subdominant saddle.
What do you mean by minus sign?
I mean the action is less than the thermal AdS.
No. Well, actually, you're right. Because
I'm looking at your paper, so I think.
Yeah. Actually, you're right. Basically, this is due to the small black holes in AdS.
Yeah.
It's actually unstable in the grand canonical ensemble, but we are now just using the index as counting the number of states, so it is perfectly okay to use this index.
Okay.
And for illustration purpose, sometimes I will unrefine the chemical potentials as like this. So this T scale will conjugate to the charge, which is nothing but the linear combination of our charges and angular momenta commute with our supercharges. So yeah, we want to study index in the BMN subsector, and we firstly we should count the number of gravitons, number of independent gravitons in this BMN subsector. And I will skip how we did this. But anyway, for SU2 theory, you can count the number of independent gravitons in the BMN subsector, and this is the result for the graviton index. Unfortunately, this closed form expression is only available for SU2, and for higher end, we only have the result until certain charge order. And you can subtract from the full index of SU2 BMN subsector, which give you the, let's say, fortuitous index of SU2 theory in BMN subsector. And if you unrefine all the chemical potentials, you will find that this index starts from charge level 24, which means that the fortuitous operators appear at this level, which was firstly found by Chiming and his colleague. So this fortuitous index has 3 factors. Actually, some of them is already explained in previous talk, but now we do not concentrate ourselves to this SU3R singlet subsector. This is the full BMN sector. So the first part, I want to interpret it as the genuinely new, the contribution from genuinely new core black hole operators. And the second factor is nothing but the superconformal descendant of these new operators. So this should be there. And the third part can be understood as the multiplication of certain graviton triplet on top of these core black hole primaries. So these 2 factors we know very well. And basically, this first factor is new, essentially new information we should explain. And after the unrefinement, you will find this series, which means that you should find unique fermionic operators at each charge level 24 plus 12n. And interestingly, it turns out that they are all SU3R singlet. So in SU2 theory, BMN subsector, these core black hole primaries are all SU3 singlet and with increasing spins. So yeah, please remember this expression for later. So in order to construct new operators, we shall use 3-dimensional vector notation for SU2 adjoint fields. And this is the expression. So at charge level 24, we found this operator to be the fortuitous operator. Here, V is nothing but the graviton operators, which we know very well. And then we multiply 2 V's, and also we multiply certain fermion triplets, and then contract all asymmetry indices. This will give you non-trivial Q cohomologies. You can show that this is Q-closed by explicit computation, and you can also show that this is Q-closed due to the SU2 trace relation. So if you consider this operator at higher end, this is not Q-closed. And also, you can show that this is not of graviton type and not Q-exact. So this is really new fortuitous operators. And one additional thing I should mention is that although we constructed it at one loop, it will not be lifted at any arbitrary higher loop level because simply there is no would-be pair operator in this charge sector. So this operator will be there at arbitrary finite coupling until strong coupling limit. So this is really the operator dual to the, let's say, black hole microstates. And then you can construct the operators which will explain this full tower of fortuitous index. Basically, you multiply trace F square on top of our threshold operator and make it Q-closed or something like that. And one interesting thing is that if you multiply any 2 of these fortuitous operators, it will become 0 by Fermi statistics. So these operators account for the SU2 BMN index. So at least in the BMN sector of the SU2 theory, we found all BPS operators accounting for the index. So we know all the operators and what we can do from this. So yeah, today I want to focus on the threshold operator. And my goal is that can we utilize some properties of these black hole operators to construct new semi-classical hairy black holes in AdS. So in order to do that, we should consider finite energy excitation outside the horizon and test whether such an excitation will be swallowed by the black holes, or can we have some stable configuration with the black holes to make a hairy black holes. So let me start from the field theory side, what we found. So if we multiply the graviton operators on top of, the chiral primary gravitons on top of the black hole threshold operator, you can show that this becomes Q-exact by explicit computation, which means that these product operators will be lifted. They become non-BPS. And also you can find similar phenomenon for other gravitons, but today I will only focus on these scalar gravitons. And now I want to consider the operators outside the BMN sector. So I want to study the conformal descendant of the scalar gravitons. So if you consider the first conformal descendant of scalar gravitons and multiply it to our threshold black hole operators, it becomes again Q-exact, meaning that it is lifted. It is non-BPS operator. But the interesting thing is that if you consider second or third or higher conformal descendant of these scalar primaries, if you multiply them to our black hole threshold operators, it is still there in the BPS spectrum. So if you consider conformal descendant with enough number of derivatives, it can grasp our threshold black hole operators to yield new non-trivial black hole operators, which I want to interpret as hairy black hole operators due to the hairy black hole microstates. Of course, this cannot explain all n equals 4 Spang-Mills index. We need to find other new core black hole operators if you go high enough orders. But anyway, these hairy black hole type cohomologies explain quite a wide range of our index. And I want to ask that can we find similar behavior from semi-classical black holes in AdS? So can we construct new supersymmetric hairy black holes based on our observation, meaning that only gravitons having large enough angular momenta can dress our black holes. So we start from the simplest BPS black holes in AdS5. It will parameterize by one free parameter. Its mass is given by the linear combination of its electric charge and angular momenta, and electric charge and angular momenta will satisfy nonlinear relation, which I showed earlier. And you can try to put the bosonic probe particle on this background dual to the chiral primary and see whether this can make a stable orbit outside the event horizon. And then what you will find is that the rotating BPS solution outside the horizon exists only when the angular momentum of this bosonic probe particle is larger than certain amount given by the black hole parameters. And of course, this can be intuitively understood because if you have small angular momentum, because of the gravitational interaction, it will be swallowed by black holes. But if you have enough large enough angular momentum, it can balance with the gravitational interaction, so you can find this stable orbit outside the event horizon. And you can promote this idea to the wave picture, so you can basically solve the complex scalar equation on top of the black hole background, assuming that their interaction is very small. So we solve it in the probe limit, and we found the BPS solution given as this. And well, it looks a bit complicated, but it can be seen quite easily since this angle-dependent part is nothing but the usual derivative factor acting on the conformal primaries. But here, if you focus on the radial part, you can see that at the horizon, the solution remains finite only for the modes when its angular momentum quantum number is larger than certain amount given by the black hole parameter. So this is in accordance with what we found in the particle picture. Only when the wave has large enough angular momentum quantum number, it can be superposed with our black holes. And this is, of course, intuitively understood. If you consider conformal primary gravitons, it prefers to be at the central region of AdS, which is hidden inside the event horizon, so it will be swallowed and bang react strongly to make it some non-supersymmetric, complicated black hole solution. However, if you consider a field with higher M, it will mostly rotate outside the horizon and can be superposed with small bang reaction, give you supersymmetric hairy black holes. So we found why conformal primary gravitons cannot be the hair of BPS black holes, and why particles with larger angular momentum can provide hair of BPS black holes. And surprisingly, these are in qualitative accordance with the behavior of CFT operator spectrum of SU2 theory. So we do really get some lessons from SU2 theory to construct new hairy black hole solution in the gravity side.
Sorry, which approximation did you use to? Which approximation did you make to construct the solution?
Basically, we neglect the bang reaction of the scalar field on the geometry. We fix the geometry and we just solve the scalar field equation in the problem. And of course, you can systematically do perturbation so that computing the bang reaction of this scalar field on the black hole geometry and considering such bang reactive geometry, bang reaction of bang reactive geometry on this scalar field and so on. But we only do the first order perturbation on this black hole background.
Try to find the full solution or not?
No. We only consider the problem limit. Yes.
Question. So you mentioned in the hypermultiplet. What do you mean exactly?
Sorry, hypermultiplet?
No, there in the slide that the small
yeah.
complex scalar in the hypermultiplet. What is the hypermultiplet?
Well, I mean, in the gravity side, you have the hypermultiplet. Yeah, and just consider Klein-Gordon equation of this complex scalar field.
Yeah, my question is, so you're committing to some model, that is you coupled, I don't know, the gauge supergravity theory to some specific model, some specific hypermultiplet? Because I would expect the construction should be general and should not be related to the uplift to S5, for instance.
Yeah, we considered some consistent truncation of, so we did our computation in 5 gauges per gravity.
Yeah, but I mean, I guess the model uses some properties of the internal space that is S5.
Yeah, you're right. I mean,
while I would expect that probably this should not be important because this phase should exist universally.
Yeah, I agree. Yeah, but yeah, for computation we use some specific models, but yeah, you do not depend on very much detail of the truncation.
Yeah, but knowing this should be important in order to possibly construct the back-reacted solution.
Sure.
If one wanted to try.
Yeah, sure, I agree.
A related question is.
A related question is: do you know what is the operator which couples to that scalar? It's a specific one.
Well, I mean, they are just conformal descendant of this phi m, or well, since we are in large n, so they are the conformal descendant of this superconformal primaries. Okay. Trace x to the some power or something.
Okay, thank you.
So we found this solution, and so this is one particular solution of supergravity, at least in the problem limit. And I'm interested in the thermodynamic problem, so I want to consider the thermal ensemble of this all-out graviton hair rotating around the core black holes. This is not very extremely strange things to consider because below the Hawking page temperature, we know that the phase, the dominant phase is nothing but the thermal ensemble of gravitons, right? And now I want to consider the thermal ensemble of allowed graviton hair rotating around our core Gutovsky-Real black holes. And this configuration, we named it as the gray galaxies. Basically, we have a core black hole at center of the AdS and surrounded by very large flat revolving disk of dilute thermal gas of gravitons so that their interaction is negligible at the leading order. However, since the radius of disk scales as n to the 1/2, you can show that the energy carried by this gas of gravitons is of order n squared, which is comparable to the charge or angular momentum of the core black holes. But still, the entropy of the rotating hair is negligible. So basically, all the entropies are carried by core black holes, but the charges are distributed between black holes and the gas. So in this way, we can construct a weakly interacting mix between black holes and graviton gas, which we call it as gray galaxies. One nice thing about this hairy black hole solution is that the gravitons need not to obey any charge relations, meaning that this type of hairy black holes can freely violate charge relation. But here we are talking about the rotating gas on top of the black hole background, meaning that we can only violate the charge relation so that our gray galaxy solution has larger angular momentum than the Gutovsky-Real or CCLP type supersymmetric black holes at given charges. Any questions about these gray galaxies? Yeah, sure.
So if you're a GR person and you write down a solution of Einstein's equations, it's solve some PDEs or whatever. It's classical physics. Mm-hmm. And then the weird thing about black holes is that they also have a thermodynamic interpretation. Mm-hmm. And this is somehow going beyond GR in the sense that you're adding a thermal gas on top. I mean, can a slightly unstable classical GR solution decay into a thermal gas? Or that sounds weird if you're just like a relativist person. But maybe the microscopic gauge theory tells you that's what's supposed to happen.
But the thing is that, we know that from the paper by Hawking and Page that if you are in very low temperature, the thermodynamic phase is really the thermal ensemble of graviton gas, right?
Yeah. Maybe it's not that
is not a
different
particular gravity solution.
Maybe I have in mind something like a little bit more advanced in which the black hole looks like a single classical solution, and then it can emit particles and turn into a thermal gray galaxy. Maybe it's not that different than the Hawking page, but maybe this is an extension of Hawking page.
Yeah, basically, well, since we are now in the BPS surface, so yes. It is not a real-time process, but you can think of it as black hole emits some thermal particles outside the event horizon to make it the thermal ensemble of gas of gravitons outside the event horizon, making gray galaxies.
Maybe I'm getting it, as was just brought up over here, that if I might be getting ahead of you, but if we're talking about the instability, which maybe you're not focusing on as much, but
I can talk about that, but
maybe
it is the final temperature problem, and if I started to talk about that, we cannot go to the reception.
Okay, all right, sorry. She shouldn't have given me the mic here.
Yeah. So we are now in BPS surface, so it is just a thermodynamic problem.
Yeah.
So then one might ask that can we violate charge relation in the opposite way? Can we find some supersymmetric hairy black holes carrying more charges than the known black holes? So this angular momentum is nothing but, of course, it's angular momentum rotating around AdS5, but our charges can be understood as angular momentum on the internal surface, internal sphere S5, right? So can we construct hairy black holes carrying charged hairs means that can we consider some dual version of rotating graviton hairs, and which we know answer very well. That is nothing but the dual giant graviton, which is D3 brane wrapping S3 of AdS5. So we have the supersymmetric black holes in the center of AdS5, and we consider large D3 branes surrounding these black holes, which we call the dual dressed black holes, basically dual giant dressing black holes. So we have a core black hole at the center of AdS surrounded by very large D3 branes whose radius scales as n to the half, so that the energy and charge is over order n squared. The entropy is n to the 0. So all the entropy is carried by core black holes, but the charges are carried by black holes and also as well as these D3 branes. And since this is very much separated, so that you can confirm that their interaction is ignorable in the large n limit. Their bang reaction is 1 over n to positive power. And yeah, so these dual dressed black holes will violate the charge relation in the opposite way of the gray galaxies. So it will carry more charges than the known supersymmetric black holes in AdS5. And so we constructed all this solution in the probe limit, and you may ask that if we consider all kind of quantum corrections to this configuration, will they remain to be BPS? Or slightly lifted to have nearly supersymmetric configuration? It is very difficult to answer it from the gravity side, since we don't know all perturbative corrections to the gravity solution. So we now go back to the field theory side and study the index, whether the index can capture this kind of hairy black hole geometries. So we again go back to the index, and now index can be thought of as -1 to the f weighted sum of partition function along the initial line parameterized by x here. So the operator, BPS operators, will carry 5 independent charges, 3 R charges and angular momentum, but index is ignorant about 1 linear combination of them, so we only have 4 independent charges, which can be seen by the index. And since index can only see 4 charges, it is also ignorant of the charge relation. Therefore, so what we want to do is analyze the microcanonical phase diagram in terms of these initial charges in the gravity side, assuming that -1 to the f does not affect the entropy at the leading order, which is true, at least true for the known supersymmetric black holes. So firstly, we search the parameter space of known BPS black holes like Gutovsky-Rado or CCLP type solutions, and you will find some interesting region, meaning that some chemical potentials become negative near the corner of parameter space when some charges become much larger than others. And using the first law of thermodynamics for the BPS black holes, you can see that emitting charges conjugate to negative chemical potential will increase the entropy. So you should find some more entropic solution than the known BPS black holes when some chemical potential become negative. So this is rough picture when you fix the angular momentum and you vary the charges. At the center, when all charges are equal, of course, the known BPS black holes are dominant. But if you go to the corner of the parameter space, you will see that there should be more entropically dominant solution than the known BPS black holes. And we can compute the entropy of our proposed hairy black holes, like dual-dressed black holes or gray galaxies. And using that, we can draw the microcanonical phase diagram in terms of initial charges. So this diagram is drawn at fixed angular momentum. So if one of, let's say, Q1 is much larger, no, Q1 and Q2 is much larger than Q3, then it is given by the dual-dressed black holes having Q1 and Q2 by large D3 branes, and so on. And here, if we fix the R charges and vary the angular momentum, and if J1 is much larger than J2, then the gray galaxy will have more entropy than the known CCLP type black holes or Gutovsky-Rad type black holes. So this is our prediction for the microcanonical phase diagram in AdS5. And now we want to test from the field theory side. So as a toy example, let us focus on the just center. So when all the charges are equal and scale the charges in equivariant way, so then we first unrefine all the chemical potentials and basically just compute the degeneracy of the index order by order. And these red and blue dots showing the log of the degeneracy captured by the index. And this black line is nothing but the entropy of the black holes extrapolated to n equals 6. And you can see that even from n equals 6, the index do match the black hole entropy very well. Great. So even from the finite n index, you can see the black hole entropy. And now we want to move to this direction so that the angular momentum, the difference between angular momentum, J1 minus J2, becomes larger. Then our prediction from the gravity side is that at a certain moment, you should find the gray contribution of the gray galaxy, which is more larger than the known black hole solution. And the result is given by this. So at small angular momentum, small difference of angular momentum, the index matches well with the known black hole solution. But if the difference between angular momentum becomes larger, you can see that the gray galaxy solution is more dominant. And if it becomes much larger, then the known solution actually doesn't exist while the gray galaxy exists. And the numerically computed index matches very well, at least qualitatively, with our gravity prediction. Matches very well to the entropy of the gray galaxies. So yeah, we do believe that gray galaxies are there in the BPS surface. So yeah, we do believe that these supersymmetric gray galaxies will not be lifted, even if you consider the stringy corrections to the classical solution. So we found, so in summary, the BPS black holes have this nonlinear charge relation, but we constructed the supersymmetric gray galaxies and real dressed black holes. And nice thing about these hairy black holes is that since this hair need not to obey the charge relation, those hairy black holes can freely violate the charge relation. So now we do have all supersymmetric black holes entirely filling this BPS surface. And yeah, actually our solution can be straightforwardly generalized to the finite temperature solution, basically replacing the core supersymmetric black holes as finite temperature black holes. And this will actually fill the gap between extremal line and the BPS surface, and also replace the near extremal black holes, which is unstable, dynamically unstable. So in certain region, we found that hairy black holes give more dominant contribution to the index, and they exist even when the non-hairy black holes do not exist. And recently, by a nice paper, and one paper by here, Venice and Finn, that the dominance in the microcanonical ensembles, actually the dominance between gray galaxies and the known black holes change precisely when the conservative Siegel-Witten criterion for the unhairy black hole, when you consider the gravitational path integral, is violated. Yeah.
How is that related to the criterion? Does it coincide, or is it different than the criterion in the Aharoni and collaborators paper about the stability of the D-branes? Is it the same?
You mean this D3 brain instantaneous instability?
Yeah, are those two criterion the same in this context?
I'm not sure, but I think that is a different thing, right?
Yeah, I think so.
Yeah, well, this is,
What do you mean by
that
different
means the solution is unstable against the condensation of these 3 brane instantons, and this criterion, I'm not familiar well, but it's about, well, whether it can contribute to the Euclidean gravitational path integral or not. So,
Oh, I interpret their criterion also as
some kind of instability?
no, I mean as a criterion of whether the saddle contributes or not to the gravitational path integral that computes the index.
Yeah, this is that criterion, but the distributing instanton case, well, they also exclude some solutions using that criterion, but I think that there's 2 different criterion, which I don't know the relation between them.
Okay. Is it stable under D3 branes in the cases that you?
No.
Because it could be that it satisfies the Kontsevich-Segal-Witten, but it's unstable under the D3 brane. For example, that I guess that's what I'm asking. Does that happen? Or no?
Actually, if this criterion is violated, the solution is unstable under the distributed instanton configuration. But you can see that the threshold line is different.
The difference between the 2 criteria?
Yeah. I mean, this is the weaker condition. Distributed instanton condensation will give you the strong condition, give more stronger condition.
So there are cases that satisfy this condition that are unstable under D3 brane?
Yeah.
Okay.
Yeah.
I see. Thank you.
Well, yeah. Basically, okay. So, yeah, the final comment I want to make is that, so when we construct this type of gray galaxies, we were inspired by the SU2 operator spectrum, SU2 fortuitous operator, the behavior of fortuitous operators. But we don't see any signal of these dual-dressed black hole type operators in SU2 theory. Why is that? So, yeah, schematically, these 2 hairy black holes look like this. So for the gray galaxies, you have SUN core black holes surrounded by thermal gas of gravitons. But if you consider the dual-dressed black holes, since the distribution is not serves as the domain for the Raman-Raman flux, meaning that if you try to construct this type of solution, the core black hole should be given as actually the black hole in SUN-1 theory. But if you consider n equals 2, it means that SU1, there is no SU1 theory. So yeah, it is expected that this type of dual-dressed type operators cannot be seen from SU2 theory. So you can ask that, can we see these operators in SU3? Yeah, so we did similar analysis for SU3 in the BMN sector, subtract the graviton index and so on, and this is the result. So this tower, these 2 numbers are nothing but the Dynkin labels for SU3. So this tower is the SU3 singlet tower, which was explained by Samuel Leuven's talk. And this is analogous to what we found in SU2 theory. So in SU2, all fortuitous, I mean, at least for the core primary, all fortuitous operators are SU3 singlet. But now we have plenty of SU3 non-singlet. So for this SU3 singlet, it was already explained how can we interpret these fortuitous operators. But if we focus on these, it is very tempting to interpret this as the dual-dressed black hole type. So you can think of it as this number as the radius of the D3 brane surrounding the black hole. So if it becomes larger, the R charge becomes larger. So, and very recently, from our colleagues, including Sierra here, he constructed that these fortuitous operators explicitly as the dual-dressed black hole type operators, as we expected from our study of SU3 fortuitous spectrum. So we do have the CFT operator also dual to the dual-dressed black hole operators, as well as the gray galaxy type operators. And one separate question you can ask is that, so basically when we construct these hairy black hole type operators, we only use the threshold operators somehow. And you may ask that, can you also construct this SU3 threshold operator? And the answer is yes, this is SU3 threshold operator if you are curious about the explicit form of such an operator. We constructed this operator, and it happens that the index chart, the threshold level is equal, but the scaling dimension is larger than the threshold operators at SU2 theory. And you can try to do similar analysis for SU4, but it is technically more and more difficult, and we could just find this two non-trivial term in the fortuitous index. One funny thing is that threshold cohomologies now are not a singlet under SU3. So let me conclude. We studied the classical cohomologies of BPS operators in n equals 4 per Yang-Mills, and yeah, for the series of talk, you heard that even at small n, we can distinguish cohomologies for the gravitons and the rest, monotone fortuitous, and fortuitous operator may describe quantum black hole microstates in AdS CFT at finite Newton constant. And in SU2 theory, we constructed an infinite family of these fortuitous operators, and we studied the hairy behavior of threshold operator, and we see that primary gravitons cannot dress the threshold operator, while the descendant operator can dress the operator. And we provide a gravity interpretation of this phenomena studying graviton hairs superposed with non-hairy black holes and constructed new supersymmetric hairy black holes, which we call BPS gray galaxies. And for SU3, we found many tower of states, and one of them are, in fact, due to our another type of supersymmetric hairy black holes that is called dual-dressed black holes. So this is a schematic summary of what we found. So we are studying the 16 BPS operators, and we have two types of BPS operators. One is monotone, and the other is fortuitous. And among fortuitous operators, we define some core black holes, and we want to study the dressing of core black holes by graviton operators. And we found that only certain gravitons are admitted to dress the core black holes, and they are actually dual to the supersymmetric, two types of supersymmetric hairy black holes we found. We call gray galaxies and dual-dressed black holes. And with these supersymmetric hairy black holes, we completely fill the BPS surface and also this finite temperature gap and unstable near extreme black holes. There are many interesting future directions. You may want to go to higher charges or higher n, or you want to go to less supersymmetric case, other space-time dimensions, or D1, D5 system, and so on. So there are many interesting models you can study this fortuitous problem. And also in the gravity side, we constructed two types of supersymmetric hairy black holes, and I showed some qualitative evidence computing the by numerically computing the index at sufficiently large n. But you may try to really construct the large n saddle point of the index dual to these hairy black holes. And also you can consider some nonlinear construction of these hairy black holes, considering bang reaction of these probe hairs. And one interesting thing is that if you consider the dual-dressed black hole type, dual-dressed black holes, since you have these three brains very far away from the black holes, this is half BPS, and you know that the bang reaction of this half BPS D3 brain is nothing but the Lin-Luny-Maldacena geometries. So maybe the nonlinear construction of dual-dressed black hole is to find some solution connecting Gutowski-Rao type black holes and half BPS LLM geometries. And one ambitious question one can make is that so basically we construct operators we believe that dual to the hairy black holes having core at having well-known core black holes, but you can ask that can fortuitous operators lead to genuinely new solutions with non-trivial horizon topology like black rings or black lenses in AdS, which we heard from Dario yesterday. And two other things I want to mention is that, so today analyzing the supercharged cohomologies, we probe the behavior of particle excitation outside the event horizon, giving rise to supersymmetric hairy black holes. But then we can ask that what can we learn about the interior of the black holes from these supercharged cohomologies? Maybe in order to answer this question, we should try to analyze the correlation function between these fortuitous and monotone operators to study quantum chaos in information problem regarding these operators. And finally, in this context, you can introduce one more interesting thing. So you can introduce AD singularity on AdS to basically this is to introduce new degrees of freedom on your quantum gravity spectrum. And they are coming from the brains wrapping the singularity. So you have now three types of degrees of freedom, basically graviton, black holes, and also brains wrapping the singularity. And this will give you topological degrees of freedom. And more interestingly, you expect in this setup, there will be two kinds of phase transition. One is usual Hawking phase transition, and the other thing is that deconfinement transition of tensionless strings on the internal S5. So it'll be also interesting to study the quantum gravity spectrum in this context. So this is all I prepared. Thank you for listening.
Questions?
I have a confusion about the comparison that you presented between the prediction from the index and the gray galaxy. So the prediction for the index, it's obtained in a regime where these chemical potentials become negative. Is it?
No. I mean, well, this microcanonical phase diagram is drawn that, so yeah, you're right that this boundary is where the...
So shouldn't the gray galaxy exist in a regime where the angular velocity becomes negative?
No. I mean, this is the line where the angular momentum chemical potential for the known black holes become zero, but for the gray galaxies, it becomes non-negative. It still remains to be zero, so there is nothing problematic here, or slightly larger than zero. So, yeah, and it'll be better to understand this diagram in the microcanonical ensemble, so that if the charge, the difference between angular momentum becomes very large, then the gray galaxy will be dominant, but if it is small, the known black hole is dominant. And this is the prediction from the gravity side here.
Okay, thanks.
Yes.
So from the product of these cohomology classes, you observe this partial no-hair property,
Yeah.
and you need to dress the black hole by operating with large enough angular momentum.
Yeah.
But from the discussion of gray galaxy,
Yeah.
I do not quite see such a gap.
Gap for what?
So, I mean, so if I start with some black hole that I leave on the black hole sheet, and then I try to dress it, I need to dress it with some operator with large enough angular momentum. So that that means I should have a gap in angular momentum.
No, I
Why
mean,
is not?
well, it is true that it should carry large enough angular momentum, but the angular momentum of the single mode is negligible in the Lorentzian limit. The angular momentum of this rotating gas carries order n square because you consider thermal ensemble of all of the hairs, but the single mode will carry n to the zeroth order angular momentum.
Yeah. Okay. From the SU2 analysis that you did, I mean everything of order one, but shouldn't we expect that this partial no-hair property, if I try to consider larger n case, then So we will see all the N of this partial no hair property.
No, I mean, you can see that the lower bound is order 1.
Okay.
I have a question that is a little bit open-ended, but so your analysis, at least on the gravity side,
Yeah.
seems completely generic. So I have a black hole, I have gas. But when we compute the index, we know it's very dimension dependent. For example, in 3D, you have you have monopoles. So there's all. So how do you? Why should we think that this is? Or do you believe this is true in all dimensions, or how do you see these index properties reflected or at all in what you're saying?
Actually, there was, I mentioned at some slide, but recently there was paper by Finn and Venus that in AdS4 they constructed this type of gray galaxy and dual-address black holes and on the gravity side and plot this similar phase diagram, and I expect similar behavior should be seen from dual field theory side computing the index. Of course, I agree that index has much different form, as you said, monopole flux and so on, but I think this picture should somehow emerge also in that case.
So if I understood that your gray galaxy is a solution in the minimal supergravity theory?
Well,
in the same theory in which the black hole exists, right? There is no additional scalars and so on, like in the other one, right? And in the center, there is the black hole with the horizon, etc. Is it supersymmetric, or you think it's supersymmetric?
It's supersymmetric.
Yeah. So these results that we have from this localization point of view, they would imply, let's say, or suggest that the action of that solution would be exactly the same as the black hole, because it depends only on the topology of the horizon, and then we have exactly the same entropy, etc.
But here I think the lesson is that, so usually when you consider the black hole solutions, usually we think that all kind of data can be read off from the near horizon region, but here now we have non-trivial hair at very far away from the horizon.
But the localization results suggest exactly that doesn't matter at all, because you only pick up the contribution from the fixed points, which are the horizons.
Well, I don't know why this does match, but here what we have done is simple. We constructed solution, and we computed the energy, and we computed the entropy. Of course, we did not compute the onshore action, so yeah.
And the entropy, you find it's different from, the entropy depends on the hair?
Well, actually, entropy is given by the entropy of core black hole. So in a sense, it is right. But the thing is that total charge is not just given by the core black holes, but carried by both of core black holes and the gas. That is the difference. But entropy is just given by the entropy of core black holes.
Okay, so maybe we can talk during the reception. Thank you.
Okay.
Hello. You mentioned black rings at the end, right? Are these supersymmetric black rings, or?
Yeah, in yesterday's talk, well, if we assume that supersymmetric black ring in AdS does exist, then the onshore action will be like this in Darius' talk, and well, maybe we can hope that really do exist, and well, it was just ambitious question. Maybe if it does exist, can we construct some new types of fortuitous operators dual to such a black object with non-trivial topology? I mean, yeah, if it is possible, it would be very interesting, of course.
If there are no more questions, let's thank the speaker again. And a couple of quick announcements. One thing is the building is locked up at 6 o'clock, so the outside doors are locked.